I'm going to talk to you about differential equations. What's a differential equation? It's an equation involving the derivative of an unknown function. And as we're going to see, to solve a differential equation, well, you've got to find this unknown function. They are very, very useful and found in many applications. A few of them are population growth, decay of radioactive material, learning curves, growth of money, earning interest, and sound waves. One example is unrestricted growth. Unrestricted growth occurs when the size of a population increases at a rate that is proportional to the size of the population itself. Therefore, the differential equation looks like this. You have a derivative, for instance dq, q is a function of t, over dt is equal to a constant times q. Here q represents the size of the population, and what we see is that the rate of change of the population is proportional to the population size itself, and the constant of proportionality is k. And in unrestricted growth, the population size grows exponentially. Therefore, we have a graph that looks like this. Another model for population growth is called restricted growth, and the differential equation for restricted growth is the following. Again, you have dqt over dt, which is equal to k times c minus qt. Therefore, the rate of change is proportional to a constant c minus qt. This constant c is called the carrying capacity, and the graph for restricted growth looks like this. So c is the carrying capacity, here it is. And the population grows and approaches the carrying capacity as t approaches infinity. So now we're going to understand what is a solution to a differential equation. Let's consider the following differential equation. Y prime minus y is equal to 0. And the function y is equal to ex. Now let's consider this function and verify that it is a solution to the differential equation. So what we do is we begin with the left-hand side of this equation. The left-hand side is equal to y prime minus y. Y prime is the derivative of the function y. The derivative of ex is ex. Y is ex. Therefore, the left-hand side of the equation is simply ex minus ex. And this here is equal to 0. Therefore, the left-hand side of the equation is equal to the right-hand side of the equation. And therefore, we can say that y is equal to ex is a solution. Note that there are other solutions. For instance, if we take the function y is equal to 2ex, and if we plug this function into the differential equation, we're going to see that it is also a solution. In this case, every solution has the form y is equal to c ex. And if we graph this, we get the following. So what we have are different curves for different values of c. For instance, this curve here, the value of c, could be equal to -1. This one here, -1/2, -1/4, and above the x-axis, c is equal to 1/4, 1/2, and 1. In this case, y is equal to cx, c times ex, which gives every solution, is called the general solution. And each curve, in this case, is called a particular solution. Therefore, a function like y is equal to -1 times ex, or y is equal to 1/2 times ex, are called particular solutions. Therefore, particular solutions are solutions which have particular values for c.